Alright, so now I'm going to go over a one sample t interval for mean. You could also call it a one sample t interval for mu, which is that symbol right there, the mu. That's what mean is. Okay, so the problem is Mrs. Cowles wanted to estimate the average weight of an Oreo cookie to determine if the average weight was less than advertised. She selected a random sample of 30 cookies and found the weight of each cookie in grams. The mean weight was 11.1921 grams with a standard deviation of 0.0817 grams. Make a 95% confidence interval to estimate the true mean weight of an Oreo. Okay, when I hear confidence interval, I panic. You should memorize that. So confidence interval, you use panic. So I'm just going to write that down. Confidence interval, use panic. Again, I'm going to reiterate which each one means. So we have P stands for parameter, which is we'll get to that in a second. A stands for assumptions or conditions that have to be met in order for you to perform or construct an interval. N stands for name of procedure, so basically this one sample t interval for mu. I stands for interval, so this is where you're calculating the interval, and then C stands for conclusion. Okay, so let's start with P. So let me do yellow, I'm gonna do P. Okay, so P is basically the parameter that you're estimating. So again, you have a population, right? A population of, let's say, all Oreo cookies, in the world, right? Or in everywhere. And we're trying to find basically the weight of one Oreo cookie, the average weight of one Oreo cookie. But because we cannot find the average weight of one Oreo cookie, which would be mu, because we can't measure all Oreo cookies. Like, we don't have that that population size. So we just take a sample, right? A sample N. In this case, we took a sample of 30 Oreo cookies, and from that sample, we calculated the mean weight, which was 11.1921 grams, right? So that was the mean weight, and because it's from a sample, this is known as a statistic, right? That's our statistic, and this statistic we're going to use to estimate the parameter, which is mu, which is the true mean Oreo weight of an Oreo cookie. So that's a little summary right there. So basically, P is your parameter, and it's what you're trying to estimate, which is mu. So mu is equal to the true mean weight of an Oreo cookie. Is that how you spell cookie? Cookie, yeah. Okay, so the true mean weight of an Oreo cookie. So that's the parameter. Moving on to the next part, which is A, assumptions. So there are 3 assumptions that you have to make in order to continue on and make a confidence interval, or basically you can think of them as conditions. I'm going to just write / conditions that have to be met. So there are 3 conditions. The first one is that the sample has to be random, and it's usually an SRS, which is a simple random sample, or it is given to you. In this case, it is given to us. It literally says a random sample of 30 cookies. Random sample of 30 cookies. So I'm just going to write right here, random sample of 30 cookies, and I'm going to say condition met. Okay, so that should satisfy that one. Second condition, also just to kind of give context, the reason this has to be random, the sample has to be random, is because if we're trying to find or to estimate the true mean Oreo weight of an Oreo, then we have to make sure it's random so that we can generalize our results to the entire population, because if it's not random, if the sample size is not random, then we can only generalize the results to that sample. So we can only say that, okay, whatever we got, like that's only going to be relevant to the sample that we chose instead of the entire population, and we're trying to find, you know, the true mean weight of the entire population. So that's why we want to make sure that the sample size is random. Okay, so number 2 is the 10% rule. So 10% rule is that the sample size is, I believe it's less than or equal to 0.10% of the population size. So 10% of the population size. In other words, in this case, the sample size is what, 30. So 30 is less than or equal to 10%, and we don't know what the population size is. We don't know how many Oreos there are. Like, we don't know the amount of all Oreos. We don't know that. So because of that, we just add our population. We just say all Oreo cookies, and we just simply say that this is reasonably true because 30 should be less than or equal to all Oreo cookies. Like, yeah, like there's there's 100,000s of Oreo cookies being sold in stores all day, and I'm pretty sure that 30 is definitely less than all of those cookies. I mean, like, what's in one box of like Oreo cookies? Like, I'm pretty sure it's, well, maybe it's less than 30, but probably like, I don't know, 20, 15. But in 2 boxes, it's definitely more than 30. So I'm sure that all Oreo cookies is greater than, even 10% of all Oreo cookies is greater than 30. So we're going to say that this is reasonably true. So we're going to say that the condition is met. Yeah, so we can't prove this like numerically. Like, we don't know what n is, so we just put the population, and then we just say it's reasonably true if it is. Now, if it's not reasonably true, you're just going to say proceed with caution, and condition not met, proceed with caution, and you're just going to continue on with the constructing a confidence interval. Okay, and then finally the last the last condition is the normality condition, or the large counts condition, or some people call it the large sample condition. So this is where n is greater than or equal to 30 only for when we're doing working with means. Okay, so let's see, n is greater than or equal to 30, or the graph, you can have like, they'll give you like the graph of the data. They'll give you the data, and then you can graph that and see if it's normal, or they'll give it to you. So they'll say this is normal, or you can just say that n is greater than or equal to 30, which it is true. Like, n is literally greater than or equal to 30 because 30 is the sample size, and it's greater than or equal to 30. So this condition is met. So I'm going to say condition met. Okay, and we use this one over here. So all 3 conditions are met. Now, to give context again, for condition number 3, if this condition is not met, then the sample size would be too small to give an accurate confidence interval. But if it's not met, we I can't say that word. People who use statistics, right, those professionals, they still continue with constructing a confidence interval, and they just say proceed with caution. But your confidence interval may not be really accurate because your sample size is small, right? If this condition is not met, because if it's not greater than or equal to 30, then, and it's less than equal to 30, less than 30, then this condition is not met, and it's like it's not normal. So it's a very small sample size to give an accurate confidence interval. But sometimes this condition is not met, but then the graph is normal. So you always want to check. If one is not met, then check the other. Obviously, if it's given, like the random condition is usually given. But yeah, this is sometimes not met, but then if you graph the data, if they give you the data and you graph it and you look at the what do you call it, the chart, you can see that it's normal, and therefore this condition is met even if n is not greater than or equal to 30. And the way you do this is by using your calculator. You would just I forgot. I think you would run a test, not a t-test, what am I saying? I think it's a t-int something. I think there's a function in there, and then you just do like second y equals, and then you just pick your graph, and then you do zoom 9, and it should like pop up there for you. But yeah, for this problem we don't need that, and it's 30, so it's obviously equal to 30, so this condition is met. Anyway, moving on. So the next thing is n. So n is the name of the procedure, and the name of the procedure, we already know it's a one sample t interval for mu. You can also say confidence interval for mu, but that's a given, you know. So that's that. Oh, I forgot in the other video to mention the other way you could do this. Maybe if I just leave a box here, I'll remember. But that has to do with the next part. So the next part is I, so panic with the I, and this is the interval. So your confidence interval is actually equal to your point estimate plus or minus your margin of error. Now, this is your general equation, right? Point estimate plus or minus margin of error for any confidence interval you're doing, but your point estimate depends on the problem and also your margin of error. So your point estimate is usually what you are, your statistic. So in other words, you can say your statistic plus or minus the margin of error is equal to confidence interval. Point estimate is your statistic. In this case, what is your statistic? Well, here your statistic is the mean that you got, right? So it's the mean. It's x bar, right? Plus or minus margin of error. What is margin of error? In this case, because we're dealing with means, we're doing t star now instead of z star. And then I'll tell you what t star is in a second, but then it's also times, I think it's the standard, what do you call it? Standard error. The standard error of x bar, right? Again, it's standard error and not standard deviation because it comes from a sample, right? We're not, all this information comes from a sample, so they're all statistics, right? That's why you have x bar instead of mu. This is why you have standard error instead of standard deviation, instead of sigma. Okay, so let's move on. So, t star is actually equal to inverse t, and it's kind of similar to z star, except there's one difference. So you still have 1 minus confidence level over 2, but then you also have this new thing called degree of freedom. So the degree of freedom is basically, how do I explain this? So it's kind of in the name. It kind of takes into account the freedom that this, how do I say it? It just, let me Google it. I don't know how to explain it. I just go with it. So, degree of freedom, meaning, so each of a number of independently variable factors affecting the range of states in which literally by the number of independent values or quantities which can be assigned to a statistical distribution. Freedom is a number of values in the final calculation of a statistic that are free to vary. Exactly, free to vary. But that doesn't make sense because then why do we do margin of error? You know what I mean? It takes into account the freedom that they have in in the distribution. I don't want to say that because I don't know if I'm sure. Yeah, well, essentially it's in the name. It's degrees of freedom. So it's taking into account the numbers in a statistic that are free to vary. So sometimes when you're doing a t-test, not a t-test, Jesus, a t-statistic, you're using t-star, okay? Sometimes when you're using t-star, numbers kind of vary, and so by using the degree of freedom, you're kind of taking into account that variation and kind of taking it out, so it's more of an accurate answer, okay? Hopefully that makes sense. But if not, just go with it, and then do your research on your own. Where even is my word? Oh, it's over here. Okay, so yeah, just go with it. And I'll tell you what degree of freedom is in a second after I plug in the rest of our information. So the standard error of x bar. The standard error of x bar is s of x, right? S of x over the square root of n, okay? So that is the standard error of x bar. So again, standard error of x bar is s of x, which is the standard deviation that is given, and then the square root of the sample size n. I don't like the way that's written. Okay. So, what are we doing again? Oh, let's plug in the numbers. Oh, actually, I didn't say what this is equal to. So, df, your degree of freedom, is equal to n minus 1. It's super simple, just subtract 1 from your sample size, okay? And inverse t is a function in your calculator, and I'll go over, I don't think I even have that, so we'll see. I'll go over everything. Okay, so your statistic, x bar, what is that? I think it was 11 point something, so let's go back up and see what it was. It was 11.1921. Plus or minus, we're going to leave this here for now, and we're just going to do the standard error of x bar, which is what? 0.0817. 0.0817. 0. Why can't I see my mouse? 0.0817 over square root of 30, because your sample size was 30. That's our standard deviation up here, s of x, and then that. Okay, now give me 1 second because I think my thing is lagging. Okay, there we go. Alright, so the way you calculate inverse t, which is not inverse t, what do you call it, t-star? In your calculator, you want to go to, let's see, second bars. I don't think I have it. Or vars, second stat. Second vars. Yeah, I don't have that. So if you have a TI-83, you don't have this function. So this is where Python comes in. So if you don't have this function in your TI-83, this is only going to help you to do your homework. Obviously, you can't have a whole computer out during your AP Stat exam, so you're going to have to borrow a TI-84, which does have inverse t. But if you don't have you don't have this function in your calculator, then I'm going to show you really quickly how to do this using Python. So basically, I'm not going to go over, maybe I should, but it's not, but I'm not going to go, actually, it's literally the same thing. It's me writing out, look, you see the same, okay, ignore the libraries, this just makes it possible so that I can use certain things here. So I said df is equal to n minus 1, we already know that. Q is basically this, so in stats sometimes you're going to see this written in a certain different way. So you're going to see this here written as Q df instead of 1 minus CL over 2. This is the same thing as Q, it's the area. So I just said Q, right? So, where is this stuff? So it's Q, right? That's the area. And then I did T star is equal to the absolute value because we take the absolute value only. Rounded for 4 decimal places. I used a Python function. You can forget about this. This is stats.t.ppf is the equivalent to inverse t in your calculator. And then Q, right? So 1 minus CL divided by 2, and then your degree of freedom, which is already stated stated above over here, right? So it already calculated for you. And inside the function, you just have to put in your confidence level, which is how confident you're going to be that whatever you're estimating is going to lie within the interval that you're calculating. In this case, it's 95%, right? I think it's 95%. Let me check. Okay, back up. Yeah, 95% confidence interval, which is your CL, right? And where are we? Oh yeah, and then your sample size, which is 30. So, right, so put in 0.95 and then put 30 and then run that, and it's going to take a little while. Just wait for a second. And it should give you your T star. And yeah, like that's what it is. And usually when you're doing a degree of freedom, you want to make sure that you say like which degree of freedom you are using, because what was I saying? Because sometimes you get different degree of freedoms, like using your calculator and doing it by hand, and so it varies the answer. So when you get an answer you want to make and you use a degree of freedom, just make sure that you stated which degree of freedom you use. So in this case, I would be saying that DF is equal to 29 in my work. So this is our T star, so it's 2.0452. So let's go back all the way up here. Let's go down. Where were we? So 2.0, I forgot already. 2.04, what? 2.0452. 0452. And I forgot how many decimal points you round it to. I don't know if it's 2. Is it 2? I think it's 2, just like these stars. So maybe I'll do 2.05. Okay. And then yeah, that's what we have so far. And then I will multiply these two numbers together. So let me do that real quick. If I can find my calculator, which is over here. Okay, so what is it? 0.0817. Are you kidding? Actually, hold on. What am I doing? See, clear. So square root of 30, right? How do you do this here? Square root 30. What? How do I do the square root? Second. Okay, what is going on? Square root. How in the world do I do this? Oh, I think you write the number first. 30 square root. Okay, there. So you take, okay, so let's do that. So you take 0.0817 and divide that by 30 square. Oh no, that's not what I meant. I meant, okay, 0.0817, divide that by 30, not 32, square root, and that's your answer. What did I do? Okay, hopefully that's our answer. I didn't mess up. So this is that number, and then just times that by 2.05, and that is 0.03057. I don't even care. I'm just gonna do 4 decimal places. That's 1, 2, 3, 4. So let's do 6, and then erase that. So we're gonna do 6, okay, and then plus or minus 11.1921. Okay, and let me just make sure that I got T star right. Hold on. 2.05. Okay, 1 second. Alright, so my T star is right. Everything is right. I'm just going to change this to a 5. I'm not going to round. For some reason, like, some teachers just don't like to round. I just don't understand. Like, some teachers tell us to round to 2 decimal places. Some teachers tell us to round to 4. It's just really confusing. And then we get different answers. But, the answer key says 5. They don't round, which is weird to me. So I don't understand. Like, okay, my teacher tells us to round. The answer key doesn't round. This is like, whatever. Okay, anyway. So we're just going to use this, but so far we're right. Let's see. Okay, so yeah, that's pretty much all there is to it. Now we just add. So we do 11.1921 plus 0.0305, right? So this is your confidence interval so far. Let me zoom in. Okay, here we go again. Okay, here we go. Okay, so when we add, that's going to be, comma, it's going to be here, so it's going to be 11.2226, and then we're going to erase that. We're going to do 11.1921 minus 0.0305. That's going to be 11.1616. And again, to make sure that you understand this, in a number line, back in 3rd grade when we learned what a number line was, start with 0 at the middle. These are negative numbers. These are positive numbers. So same thing with the confidence interval. You want to use the smallest one first and then the biggest one. So you want to, when you subtract this number from this number, you want to put it here, the answer. And when you add this number to this number, you want to put the answer here, okay? So that's what it is. So it's going from basically from least, okay, now it doesn't want to write again, to greatest. Okay, so that's how it goes. That's your confidence interval. Now, let's move on to C, okay? So what does this mean, basically? I'm just going to do it on this side here. So what does this mean? So for C is the conclusion. I do y, okay, the conclusion. So again, we are blank percent, so this is your CL, okay? 95% confident that the interval from, what's our interval? 11.1616, 11.226 captures the true mean Oreo weight. Yeah, that's pretty much it. That's their conclusion. So we are 95% confident that the interval from, this is our interval, captures the true mean Oreo weight, which is our context, right? Yeah, so that's all there is to it. Oh my god, I knew it was worth it. Thank god I put that box there. So, here's a little loophole. If you don't remember the name of your procedure, you can simply plug in, where is it? This. Well, this, but, okay, let me just write it here. You can plug in 11.1921 plus or minus inverse t 1 minus 0.95 divided by 2, 29, because data frame is 30 minus 1, which is 29, and then times 0.0817 divided by square root 30. This right here, let me figure out where the eraser is. This right here is the alternative to saying this. I mean, you're gonna have to have this either way, and you're gonna have to know this to even know what you're, what margin of error you're gonna use. So, I don't know, it's to each their own. So, yeah, this is the alternative. If you can't remember what the procedure is called, you can just write the formula with the numbers plugged in. It just can't be, you can't just write this and you can't just write this. You have to write this right here with the numbers plugged in. I didn't write this specific here because I didn't plug in the numbers. I forgot to plug in the numbers there. But yeah, confidence level is 0.95. Let me just write that down over here. So this is again confidence level. Yeah, I think that's pretty much it. Again, if you have your TI 84, you can use your calculator. I'm pretty sure it's second VARs. It's the same place. You could just look it up at YouTube. I think it's the same place where the other one is. What is it? Inverse one, maybe, I don't know. You can use your calculator. This is one method. You can use a Z table. That's a nightmare. Or you can use technology, but you won't be able to use technology during your AP test. But you can use technology in real life. So that works for me. So I used Python. I think I used the SciPy library and the math library. But that doesn't matter. Just copy and paste my code into Google Collaboratory or Deep Notes Notebook. Just search up deepnotes.com or just use the Google Collaboratory from Google, and just plug in my code, and then you can just check your answer there. That's for T-Star. And then, yeah, this is what there is to it. Here's a little zoom out right there. I think so that's pretty much it. Oh, and almost forgot. I also have, not only do I have like the T-star function, but I also have the function that will literally just print out the confidence interval for you. So, you could just copy and paste. Oh, how are you supposed to copy and paste if you don't have the link to it? I'll post this link. I'll post this link on the description. And if you want, not like anybody watches this video, but whatever, you could just, it will be there, okay? It will be there for me, for future me, when I need to go back to these videos to relearn how to do this. So it takes in your N, your statistic, which is your X bar, your confidence level, which is 0.95, and your standard deviation, which is 0.0817, which is given to you. This is also given to you. This is given to you too. Everything is given to you, and you just put those in right here. You call the function and you just click on run, and it'll give you your confidence interval, right? So it's the same math that we did except in words, so again, just so you could see that confirm my work. See, we got a confidence interval of 11.1616, and then over here we have 11.1611, which is pretty close. And then we have 11.2226, and then over here we have 11.2231, which is, it depends. Okay, so that's fine. Again, we just did df is equal to n minus 1, like we stated what it was. Point estimate is equal to x bar, which is our statistic. Standard error of x is equal to the standard error of x, so standard deviation of x divided by the math by square root of n, right, which is math.square root in Python. Don't worry about that. Don't worry about the libraries or anything. Then we have the T-star, how to calculate T-star, which, we did it over here, but I just simply used a function, right? So I used a function and I just wrote those things in general. I could have done like Q is equal to 1 CL and then put Q here instead, but like no. I just put it in there like it is, divided by 2, degree of freedom. I did define degree of freedom over here, okay? So it's going to take n, which is 30, subtracted by 1, and it's going to set the degree of freedom to be 29, so that's what it is. And the margin of error is equal to basically T-star times standard error of x bar, which we discussed already, and then rounded by 3 decimal places, and then it's just going to add and subtract the point estimate from the margin of error, and then this basically is telling it to print this, and then we just call what we have, and then that's a way to check your answer. So I think that's the last thing that I wanted to say. probably. I don't know. Let me think. How about many interpreting like the confidence level? So many samples or trials. 95% of the samples will. No, that's for p-value. No, assuming. Yeah, never mind. Okay, yeah, this is what I wanted to say. And yeah, that's pretty much all there is to it. Bye.